Hello, chemists. This is Ms. Placino, and you're watching lesson 11.2 on rate laws. In today's lesson, we're going to talk about what rate laws are and what information they provide. Heads up, this is a more advanced topic, so if you feel yourself being kind of confused and struggling a little bit as we're going through it, don't beat yourself up. Hang in there, keep practicing, you will get better at this. Goals for today's lesson. You should be able to write the general rate law expression for a reaction. You should be able to find the order of a reaction based on each reactant. You should be able to solve for the rate constant and predict the rate of a reaction when given concentrations. If you're looking over this and you are feeling confused, don't stress. We will get you through it, and I promise it'll make a lot more sense by the end of the lesson. All right. So we're studying chemical kinetics right now, and we know from the previous lesson there are 6 different ways to impact the rate of a reaction. We can change temperature, pressure, surface area, concentration, the nature of a reactant, and we can catalyze a reaction. When it comes to rate laws, we're going to focus in on only one of those factors. Rate laws numerically describe how the rate of a reaction varies with the concentrations of the reactants. So this means that temperature, pressure, surface area, so on and so forth, play no role in rate laws. We're going to kind of set those values and leave them alone. That way, as rate changes, we know that it must be because we are altering the concentration of a reactant. We know, generally speaking, as concentration increases, the rate of that reaction should increase as well. Rate laws are going to provide us with some insight into how much the rate would increase or how much the rate would just simply change based on concentration. It's worth pointing out that rate laws have to be determined experimentally. You gotta roll up your sleeves, put on your lab goggles, and kind of get to work conducting experiments. There's no way just to look at a chemical reaction and kind of know what order reaction it's going to be. You have to run some experiments. So in our case, of course, we can't do that on the PowerPoint. So we're going to be looking at theoretical data that's been collected, and our job is going to be to analyze it. A little bit more about rate law before we start solving problems. I want to talk about the general format of a rate law expression. If we're looking at this very generic reaction, reactants A plus B yield product Z. My rate law would look something like this. The rate of the reaction is equal to K times concentration of A to the N times the concentration of B to the M. This might look completely foreign to you. Don't panic. K is rate constant. So this is going to be different for different reactions, but once you've figured out the rate constant, it will remain the same for whatever reaction you are studying. A and B in those square brackets represent the concentrations of those two reactants in terms of molarity. N and M are the order of the reaction according to that particular reactant. Basically, the value of N and M kind of tell you what impact changing the concentration of that reactant is going to have on the overall rate or the overall speed of the reaction you are studying. So our job is going to be to figure out what N and M are by looking at data. We can continue to use the data to find the rate constant. And then once we've found the rate constant and we know the order of the reaction according to each reactant, we should be able to predict what the new rate will be when we have different concentrations of A and B. I know it sounds like a lot, but stay with me. All right, before we try to put any of this information to work, let's dig in a little bit deeper about what the order of a reaction actually is. All right, so when we go to determine the order, what we do is make a change in the concentration to one of our reactants, and we see how the rate of the reaction responds. So for example, let's say you change the concentration of one of the reactants and absolutely nothing happens to the rate. So for example, you double the concentration of a reactant, but the rate remains the same. We would say that that is zero order. There seems to be no relationship between the concentration of that reactant and the rate of the reaction that you are studying. If you change the concentration by some factor and the rate changes by the same amount, so for example, you double the concentration of a reactant and the rate also doubles, we say that's first order. And finally, if you change the concentration and the rate changes by a factor of x squared. So let's say you triple the concentration of one of your reactants and the rate increases by 9-fold. So we put 3 in for x, 3 squared equals 9. That is representative of a second order reaction. There are negative orders possible, there are fractional orders possible. We're going to keep it relatively straightforward and for the most part play around with just these 3. I know this looks confusing, but I think it makes more sense when we start putting it into practice. So let's get into your practice problems and kind of walk through some of these together. Okay, so we're going to be looking at this reaction here. F2 reacts with 2ClO to produce 2FClO. We've got some experimental data. We see that the chemist has run 3 different experiments, and they've changed the concentrations of F2ClO, and then they've measured the rate of that reaction. So if we're going to try to find the order of the reaction according to each reactant, we're going to have to start to compare some of the experiments. What we want to do if we want to find the order of F2 is to find 2 experiments where the concentration of F2 changes, and the concentration of our other reactant is constant. That way, any change that occurs in the rate, we know is because the concentration of F2 changed. What 2 experiments should we look at in this case? Experiments 1 and 2 seem to fit that description. We've got the concentration of F2 doubling, and we see the concentration of, the rate, going up by a factor of 4. The concentration of F2 doubles, the rate of the reaction quadruples. So which order does that sound like? 0, 1, or 2? Yeah, this is a second order reaction in terms of F2. Let's go through that same procedure with the other reactant. We want to find 2 reactions where the concentration of ClO changes and F2 stays the same. In this case, 1 and 3 look like our best bet. As we go from 1 to 3, the concentration of ClO goes up by a factor of 4, and the rate also goes up by a factor of 4. So we would say this reaction is first order in terms of ClO. When I go to write my rate law, they're all going to take on the same format. Rate, being stubborn, there we go, is equal to some constant, K, times the concentration of F2 to the second, times the concentration of ClO to the first. Now I know that that 1 is not really required to be there. It's implied that it is a power or an exponent of 1 if you don't write anything. But when you go to find the overall order of the reaction, it's often helpful to have it written there. The overall order is found just by adding up the orders for the individual reactants. So in this case, the overall order of this reaction is 3. It's a third order reaction. You can imagine if you didn't write that 1 there, you might be prone to forget that it's there and mistakenly call this a second order reaction. All right. In my opinion, that is kind of the trickiest aspect of this whole process. You've really got to look at those experiments. You've got to find the relationship between concentration and rate. You've got to figure out the order. You've got to then kind of slam it into this format for the rate law. From there, everything else is really plug and chug. So the next question I could ask you is to find the value of K. Find the rate law constant for this particular reaction. You're going to choose an experiment and plug in the values. Does it matter which experiment I choose? No. The rate law constant, K, should be the same for the same reaction under the same conditions. So it really shouldn't matter whether you choose reaction 1, 2, or 3 to work with. You should end up with the same value. So what I want to do is take my rate law equation, I'll rewrite it. I'm going to just plug in I'll choose experiment 2 just because I can see that data. So I know that the rate is 0.0048 molar per second. I'm trying to solve for K. I've got the concentration of F2 at 0.20 molar. I know that's going to be squared. And the concentration of ClO is at 0.10 molar to the first. If you grind through that calculation, and again, it doesn't matter if you use experiments 1, 2, or 3, you should arrive at the same answer. Hopefully you're calculating that K is equal to 12. The units for K really depend on the order of the reaction. So units can be a little tricky to figure out. On the left side of the equation, I've got my rate, and that's in terms of molar over second. And on the right side of the equation, I've got molar squared times molar, so molar cubed. And I need to get to molar over second. The only way to do that is to use the units that look like this. 1 over molar squared times seconds. Don't memorize that unit because it's not always going to be the same. What you can do they're always going to be 1 over molar to the overall order minus 1 times whatever time unit is being used. So in this case, we're talking about molars per second. You can see it up here in the table. But it is possible to look at like molar per minute or molar per hour, whatever the case may be. So I knew that this was a third order reaction. I can take 1 over the molarity, overall order minus 1, so 3 minus 1 is 2, times my unit for time. It's just going to take some practice. You will get more comfortable with it. The last type of question I can ask you about is to give you new concentrations for the reactants and have you try to predict what the rate will be. How do you think you might go about solving that problem? Yeah, if you think about it, you've kind of got all the information you need. You've gone ahead and figured out the value of K. We know that's going to stay the same for this reaction. So we can plug all of the values and concentrations into the rate law and solve for the rate. All right. So you've done all the hard work already. We know that rate is equal to K times the concentration of F2 squared times the concentration of ClO to the first. This time I'm solving for the rate. I can take my constant. I already figured that out. I can multiply it by my new concentration of F2. And my new concentration of ClO. And now it's just a math problem. So go ahead, plug in those numbers, come up with a rate. I'm calculating my rate to be equal to 0.0324. What are my units going to be here? Now you can kind of go through and solve them if you'd like, but you can also remember that they're going to be provided in the data table. So my rate, if I increase the concentrations to 0.3 and 0.03, should be 0.0324 molar per second. So our units for the rate are provided in the data table. And that's really the whole process. First thing you always want to do is go through, use the data provided to find the orders. Again, in my opinion, that is the most challenging aspect of these problems. Once you've got the orders, hard work for the most part is over. I can ask you to find the value of K, which really just requires you plugging in the numbers from any of the experiments. It doesn't matter which one, they should be constant. to solve for K. Be careful with the units for K. They can be a little tricky. Once you know the value of K, that's going to remain the same for that reaction. I can ask you to predict what the rate will be with a new set of concentrations. Again, you've got all the information you need. You've solved for K, you know the orders, so you can really just take the new concentrations along with the rate constant that you figured out from the previous step, and you can plug them into the equation. Solve for the rate. You can figure out your units for the rate, kind of by making things cancel, or they are provided in the data table. This is definitely something that's going to require some practice for you to get comfortable with. So don't beat yourself up if you're feeling a little bit lost. Just keep working through the problems, check your work, and you will get the hang of this. All right, chemists, really good job with this today. This is a tough topic. So thank you for tuning in, and I hope you found this helpful.